Okay, so this is David Jensen from University of Amherst, Massachusetts at Amherst. He did his PhD at Washington in St. Louis. And after that, he went to the Congressional Office for Technology Assessment, where he actually worked on money laundering, which inspired some of the work that he's done since then, and in fact, some of the work he'll talk about today. He's the director of the Knowledge Discovery Laboratory at Amherst. And he's going to tell us about exploiting statistical dependencies in networks.
Thank you very much. Very, very happy to be here today. I've had all sorts of interesting research discussions, so I hope that I can, kind of give back some of the some ideas here, or some things that we've worked on. And please, if you have any questions during the talk, please. But if waving at me doesn't catch my eye, then please. Say something, because I'm very happy to have this be interactive. So I'm going to talk today about work that we've been doing in my group on analyzing networks. And it may seem a little odd to come here and talk about these things, because primarily I'm going to be talking about networks of entities that are known. So real physical things in the world, people, places, things, events. Not words and documents, but much of the stuff that I'll be talking about today, if your interest is in language, I think is applicable, and particularly, over and over again, I know in computer science, we represent things as networks because we want to represent things, and we want to represent relations among those, and we have this sense that, that those relations are important, and that finding out what's connected to something else is informative to predicting things about those entities. And so I'll try to draw connections to language for those of you whose interest is there, but I'll also talk about some of the work that we've been doing that has an example on other things that I think is applicable. This is a network I'll return to, but it illustrates several basic things that I'll be talking about. One is that if you look at color and have a sense that color is some sort of meaningful attribute on nodes, that nodes that are connected tend to have the same color. Okay? Talk about this as autocorrelation or homophily. Also, paths are of interest, particularly short paths, and that short paths can be found by exploiting this information that you have about homophily, about the likelihood that two things that are connected will also have the same value of the attribute. Okay, so the roadmap for today, what I'll be talking about, are really three topics: modeling networks, navigation in networks, and indexing in networks. Now this may seem like a sort of grab bag of topics, that I'm talking about all the cool stuff we've done recently. But really, I've come to the conclusion that these things are related, they're pieces of work that followed from each other, and they're joined by some common topics, which are relational dependencies, dependencies that span these links between entities, and graph structure, the idea that graph structure overall is important. Now, the modeling work is about relational dependency networks. That was done with my student, Jen Neville. She's now on faculty at Purdue, both in computer science and statistics. Those are the papers that are relevant here. And all these papers can be found on the website. The work on navigation we call expected value navigation, done with Özgür Şimşek here, student of mine, reported at ICHCAI in 2005. And finally, the work on indexing was done with two of my students, Matt Radigan and Mark Mayer. And these are specifically what we call network structure indexes, ways of indexing the graph structure. And what's fascinating is that the work on modeling led us to the understanding that we needed for expected value navigation, which led us to work on how to create these indices, which in turn allow us to create better models. And I'll give you the sense of that full kind of cycle as we go through the talk. So let me talk about modeling, specifically these relational dependency networks. I'm going to start with an example, not money laundering, which was very interesting, but a related example about financial fraud, detecting financial fraud. About 3 years ago, the National Association of Securities Dealers came to us and said, we want to analyze the network of stockbrokers in the US because their mission at NASD is to detect financial fraud, to try to protect us, the public, the investing public, from the very small number of brokers who do some kind of fraudulent activity every year. And they monitor a huge number of brokers, about 600,000, that are located in a smaller number, fortunately, of firms and branches. But their idea was that brokers tend to influence each other. Either they keep each other honest, or they teach each other how to engage in financial fraud. So if you could look at the social or organizational network of brokers, you could do a better job of predicting fraud. And they went to DARPA and said, you know, we hear you're doing work in this area, who should we talk to? And DARPA sent them to me, and then the funny thing was that I found out that one of the people that was looking for work in this, looking for somebody who did work in this area was a personal friend, Henry Goldberg, which was really very nice because that meant that we could do some really interesting work. And we're continuing to work with them. So let me tell you a little bit about NASD's problem. So fortunately, as I said, financial fraud is rare. Large numbers of brokers, relatively small numbers of them doing anything wrong. In a given year, far less than 1% of all brokers do anything illegitimate. Now, the basic idea is that we want to take data from 1995 to 2005, let's say, a period of time, for which we know some things about, not fraud per se, but about some indicators of fraud that only show up a little bit later. And then we'd like to form models of that fraud, of that activity, and then use that to infer for the future who NASD may want to pay greater attention to. Now, in no way are we saying this person's going to commit fraud. Rather, we're saying this person is a higher risk for committing fraud, and so you ought to give them perhaps some heightened scrutiny, as at the Securities and Exchange Commission and NASD say. That's somebody you should pay a little bit more attention to, or maybe perhaps pay more attention to firms that have larger numbers of these high-risk brokers in them. Now, what do we have in terms of data? Well, we certainly have a bunch of brokers. We know about 600,000 brokers. And 1.2 million in the entire data set if you go back in time, so a very large number of brokers. But fortunately, we also know a much more important thing about them, which is the network that connects them. We have branches that brokers work for. We have firms that those branches are part of. And we have disclosures. And disclosures are reports that are filed by firms and by brokers themselves on their activities when those activities are something that NASD might be interested in. So for instance, if they get a financial lien against them, if they have to declare bankruptcy, if they commit a felony. And it can be as small as a customer has complained about them. So range of different types of disclosures that give us a sense of what those brokers are doing. So you can think of these as event or activity reports. And we also have, importantly, those individual records allow us to form professional or organizational networks.
D stands for disclosure.
Correct. D stands for disclosure.
And if he has 4, then there are 4 different ones, different
Right.
type.
Exactly. And disclosures are almost always on an individual, even though you could imagine there might be multiple people involved in something that would result in multiple disclosures. Any other questions? Okay, so.
I'm sorry, a broker is a firm, right? So there might be 7 different humans.
No, a broker, what I'm calling a broker here is actually a person. Now, to use NASD's terminology, they will refer to them as a registered representative. But I'm using here the more colloquial term, broker, to refer to an individual. To be specific, they're called registered reps. And so the people you saw there are the reps, and you could say the brokers are equivalent to the firms. Now, we'd like to make predictions about probability of having certain types of disclosures, given the characteristics of that broker, that person, and the organizational context in which they exist. Things about the branch, the firm, the other brokers with whom they work. Now, why should this be hard? Well, let me tell you a little bit about why it's hard.
Actually, Dave, before I go on, another question. In the previous picture, there was no notion of time.
Right.
But you said you have 2 years worth of data. So where is time on this?
Actually, we have 15 years worth of data.
Oh yeah, 95.
Right, right. And it actually goes back further than that, but there's some data problems back really far, so we're sort of cutting that off. So yes, absolutely. Each of these employment relations has a temporal period over which it happens. and disclosures are filed at particular times.
Right.
And actually branches go away and firms go away and are formed. And all of that, yeah, definitely is in the data.
So
I'm glossing over that a little
So
bit.
could I think of this as one snapshot of a time series?
Absolutely, yeah. So this is current time, what's happened, although these would be in the past, clearly.
And who disclosed the disclosure?
Either the individual human broker, the
Said,
person,
I have been
or
conducting fraud. I mean,
No.
Yes, you have, Fred.
So here's what they do. They say, I have had a financial lien filed against me. I have had a customer complaint against me. Now, also, the firm will file these because there are very heavy penalties, either on a firm or on an individual registered rep, for not filing these disclosures. The penalties are so large that they will voluntarily file them on themselves. Now, this is shocking on one level. You think this is all voluntarily provided data, but it's not quite as voluntary as you might think. And it's also, the firms know that they would rather sacrifice a registered rep than have their own name blackened. So they're fairly good about filing these things. So that's yeah, it's a noisy indicator, but it's nonetheless an indicator of fraud. Also, some of the disclosures are filed by a firm saying, we fired this guy. He was doing something, actually they don't say that, they say, we fired him for cause, and that's all we're telling you. But usually that means they were doing something that was going to violate NASD rules. So let's presume that we have rows here representing reps, okay, individual people, brokers, and columns representing variables, standard setup for a data set. We have lots of methods that have been developed over the many decades for finding statistical dependencies between variables of a single instance, all right? Of instances assuming that they are independent and identically distributed. Unfortunately, what we have in this case is not just one kind of entity and dependencies that span entities. So you can think of there being multiple tables, not just two, but several. One table here would correspond to one entity type. So reps, firms, branches, disclosures. And we know that there are statistical dependencies that run from one type of object, a variable on one object, to a variable on another object, and also dependencies that go between instances of the same type of object. So the behavior of one rep will influence the behavior of another. The probability of a serious disclosure from one rep will influence the probability of those kinds of disclosures on other reps with whom they work, for instance. Now, these are not the type of dependencies that we typically find in things like Bayes nets and other, lots of other technologies that have been developed for statistical modeling. So this is an issue, and for those of you who know about spatial statistics or temporal statistics where you say, hey, we actually have some methods here, there's an additional problem, which is that the graph structure relating instances is not regular. Some branches have many brokers who work for them. Some have only a few. So there's an irregular graph structure here that we need to somehow analyze and understand the dependencies, the statistical dependencies that can run between these variables on these entities. Now, why is that difficult? Let me give you some examples. One, I think, fairly easy thing to understand, one of the more easy to understand influences is autocorrelation. So let's say we have these green things that are groups, you could think of them as branches, and these blue things which are members of the group, you could say they're brokers. So, and we have some attribute represented by a circle here on the brokers. And what we want to ask is there something about the group that influences the probability, the distribution of this variable on members? So the question is, if we're going to try to evaluate that dependence, what's our sample size? Is it the number of group member pairs, or is it the number of groups? Well, if these values are independent given group, then the number of group member pairs would be your sample size. But if there's strong autocorrelation that these values tend to be the same, imagine if they were all exactly the same, then you would say, well, all we need to know is group to know this value, and sample size is actually the number of groups, not the number of members. So just something as simple as assessing the statistical dependence between two variables is influenced by knowing something about graph structure. We've looked at this relationship, and if you look at a measure of autocorrelation and a measure of the kind of graph structure, and the z-axis here is sample size, as these things go up, as the graph structure becomes more highly concentrated and autocorrelation becomes higher, your effective sample size, how many data points you, essentially the number of data points you have goes down dramatically. Even though you think you have 1,000 data points, you actually have around 100. So this can have very strong influences on your ability to, for instance, determine statistical significance. Okay, and we can account for this various ways. You can do data sampling, where you try to form semi-independent instances. You can also do some adjustments to the individual scores. We've done a little bit of that. And you can also use Monte Carlo or permutation tests to try to find the correct empirical score distributions that accounts for the effective sample size. And all of these slides will be available, so if anybody's interested, you can go back to the stuff and I can point you to the specific papers if the little reference doesn't do enough. Okay, so we'd like to form statistical models, and we have methods for dealing with some of the unique characteristics of analyzing graphs. And what we end up doing is forming, for instance, these tree-structured models. Unfortunately, the edges are a little vague here, but this is a standard sort of classification tree, many of you may be familiar with, that has been modified to allow you to look at attributes of related instances. So this is just to show you the overall structure. What you do is you take, for instance, a broker and their surrounding neighborhood, their graph structure that's around them. So the things that might influence their probability of committing fraud, you drop them in the top. It rattles down through a series of questions and eventually gets to a leaf node that gives you a probability that in the next 12 months they're going to commit some kind of serious fraud. Okay? Let me zoom in on a portion of it. So the first question we ask is, how old is the broker? This is an example, by the way, not an actual tree we learned, because NASD has asked us not to show the actual trees that we learned, so you can understand why.
Is there a simple relationship between this and the trees that you did?
No. This is entirely notional, okay? But I'll show you performance results in a minute. So you drop a broker in the top. You ask, are they older than 27? If the answer is no, you go down the left-hand branch, or right-hand branch. Then you say, does their current firm, the firm they currently work for, have more than 12 brokers in it? If the answer is yes, no, you go down the right-hand branch. How many past coworkers have they had at all their previous branches? Is it more than 35? If the answer is yes, you go down here, and this is the probability distribution shown by the relative size of the red and blue parts. That's a probability distribution over their probability of committing fraud, serious fraud, or having one of these serious disclosures in the next 12 months. So that gives you a sense of the sort of conditional models that we're creating. Conditional probability model learned on the data. All right, so we can do that. Another question is, how well do these things work? So this is an ROC curve. Are people moderately familiar with what ROC curves are? Yes, I'm getting lots of, okay, good. What you'd like, of course, a perfect ROC curve would shoot all the way up here and then shoot over. The diagonal line is random performance. And we're doing better than random. This is the red here, the red dotted line, is a base level classifier that basically does not use the innovations in relational learning that we've developed over the past several years. The blue line is what happens if you do use those. RPT, relational probability tree, the type of model I showed you a minute ago. Now, what's this X? This X is NASD's current expert-derived rules. So a bunch of their examiners who know fraud said, well, how can we try to find high-risk brokers as a starting point for us to do more investigation? And it's a set of rules that basically kicks out a list. The list is maybe 200 brokers long. That identifies a point in ROC space, and that's what this is. So informally, you can look at this and say, hey, they're doing about as well as NASD's expert-derived rules. Not bad. What's nice though is that we can do a complete rank ordering over all brokers. So let's say they wanted more than 200, no problem, go on up the list. Maybe you want 100, you know which of these might be the highest probability brokers for having one of these disclosures in the next 12 months.
I want to interrupt you a minute. Could you go back one slide? Are you going to tell us how you get that probability?
That's estimated from the data. This is a standard recursive partitioning algorithm.
But you'd need to know the dependent structure in order to actually put a probability on there. Because if 50 people fall into that leaf and
Yep.
20 are fraud, then you'd call it 20 over 50, but not if you have dependents. If the 20 are all from one firm, that's not the right number.
Exactly. And these dependencies, okay, these
conditioning.
choices are conditioned
Right.
on, are ranked in a way that we think is accounting for
Okay,
autocorrelation.
you've already done that, all right.
Yeah. So another way of looking at these, the results, is to see what examiners think of them, see what the human experts think of them. So what we did was we took our ranking and we took NASD's list and we said they put out 200 brokers, we're going to put out our top 200. Now we're going to pick from these groups and we're going to pick some that occur in both lists, some that occur in only one list, and some that occur in neither list. And this is going to be done double blind. My students did it, but then I got the list and I didn't know which was which. And I set it up and sent them to the examiners who had no idea which list the individual brokers came from. And then they did an intensive evaluation, which was about an hour per broker. So they looked at each one of these for about an hour with lots of data that we didn't have access to say how bad is this individual? How much would we have wanted to know about this individual, given that we now have a lot more data because we predicted for 2006, even though we didn't have the 2005, even though we didn't have the 2005 data. And then they did have data for what happened in 2005. So they could actually look at it and see what the people did and say, how much would we have wanted to know about that? Rate them on a 1 to 5 scale. 3 examiners did this independently. 4 examiners did this independently. They looked at these and then ranked ordered them on a 1 to 5 scale. So here's what we got. If you look at the distributions of the mean rating, 5 is really bad, 1 is very good. We shouldn't, basically 1 is we never want to see this guy, 5 is wow, really want to see this. And the plot that's all the way over by 1 is it occurred on neither list. The plot on the red and the blue is occurred on either, blue is the relational models, red is NASD's current rules, essentially the same. And if they occur on both lists, then they're better than any of those. So this was really good news. We're certainly doing better than random, and we're doing about as well, again, about as well as NASD's own rules do. We also got one really nice email from one of the examiners, unsolicited by us, who said, one broker I was confident in rating a 5. Not only did I have the pleasure of meeting him at a shady warehouse location in New Jersey, in a sting operation, it turns out, I negotiated his bar from the industry. He actually used investors' funds, fraudulently obtained, to pay for personal expenses, including his trip to an NASD compliance conference. If the model predicted this person, it'll be right on target, he said. And I thought, oh, damn. Well, let's go look and see what we get. Looked him up. We predicted him. He was definitely in our top list, okay, in our above the threshold, so we would have predicted him, and he was not on NASD's list. And I swear this is the only one that we got informal feedback on. I'm not cherry picking here. It was really very nice. It was a nice sort of anecdotal thing that our model said, boy, there's really serious problems with this guy. All right, so now what can we do? We've talked about a conditional model. I'm going to mention briefly some work that we've done on joint modeling, joint model of all of the variables among the entities. And this is a relational dependency network. I'm not going to go into a lot of detail about these, but here these plates represent entities, firms, brokers, disclosures, and branches. And obviously circles, nodes in the network represent variables, and these indicate statistical dependence. Now this is not a Bayes net. This is a dependency network, some work done by David Heckerman and company about 2000. We're taking that was on IID data, we're taking that and making relational dependency networks. But what's nice about these is they give you a sense of where the statistical dependence is, even though often direction is incorrect, or at least not definitive. Here, for instance, it says things like, if the firm is experiencing layoffs, they're often on NASD's watch list. NASD is a list of firms to keep an eye on. Well, turns out that NASD defines their watch list as being partially about whether the firm has had layoffs. So NASD staff looked at this and said, big surprise, but we said, yeah, got it right without actually knowing this. Some other things are really obvious. This says that the number of brokers, not some variable, but just the raw number of brokers influences the size of a firm. Not too surprising, but also nice that the model finds it. But there are other dependencies that were interesting and surprising to NASD examiners, specifically things about, for instance, the area, this is area code, of a branch affects whether they're on NASD's watch list. And that was definitely confirmed by individual examiners who said, yeah, those are areas that have just a much higher density of fraudulent firms. The way that we learn these relational dependency networks, these are pseudo-likelihood models. What you do is you learn a set of conditional models, you assemble them then into a representation of the joint distribution. And under the assumption of Gibbs sampling, these will give consistent estimates of the joint distribution.
Do you have loops?
Excuse me?
Do you have loops?
Yes, you can have loops, and again, Gibbs sampling, under the assumption of Gibbs sampling, you can do that. These are not showing you conditional independence. It's not a standard Bayes net. I will refer you to the Heckerman paper, or we can talk after about the specific semantics of dependency networks. We've learned some other dependency networks here on the Internet Movie Database, actors, movies, studios, directors. Here about citations, citation networks in computer science journals saying nice things like the topic of a paper is related to the prefix on journals. So for instance, if it says theory of, they're more likely to be papers about theory. And things like the average rank of an author depends on the average rank of other authors that they have on the same paper. So co-authors. So people who are highly ranked tend to co-author with people who are highly ranked. Not a big surprise there. Okay, so that's the work on statistical modeling in networks, modeling the attributes of networks. Some of the dependencies that we learned are these autocorrelation dependencies. That is, that for instance, brokers tend to work if they're honest, if they don't have disconcerting disclosures, they tend to work with other people who don't have disconcerting disclosures, and vice versa. Directors tend to make movies that are of the same genre. So there's autocorrelation among the movie genres of movies made by the same director, and there is correlation among the topics of papers written by the same author. These sort of autocorrelation dependencies show up all the time in our work on probabilistic modeling. Now, this was the genesis of an idea about how to solve a seemingly really unrelated problem. And here's the problem. This was work done by Travers and Milgram. Milgram, a very well-known social scientist in the 60s, 70s, and 80s. Travers, a student of Milgram's, did this study where they gave letters addressed to people in Boston who had a name, an occupation, and a city. They were given to people in Nebraska and Kansas, and those people were asked to get the letters to the people on the front of the envelope by giving them to a first name acquaintance, someone you knew on a first name basis, and then give the same directions to those people. So you're trying to navigate through the social network to get this letter where it needs to go. Distributed navigation problem, you can think about it.
So this is a hand carry.
This is hand carry, yes.
Not
Actually, you
even-
can send it, but you have to know the person you're sending it to
I see.
in a first name basis. Yeah.
But eventually, somebody from Boston can send it to Joe
It's
Smith.
what you'd hope. Yes. So this guy says, I don't know Joe Smith, a stockbroker in Boston, but I have some friends who maybe I can give it to. I'll give it to a friend and I'll choose one of my friends and maybe they can get it to them. And then that person says, well, I'll choose one of my friends and send it to them. And eventually it gets to the goal. You hope. Now it turns out not all of them got to the goal, but a surprising number of them did. And in a small number of hops. The median number of hops was 6, leading to the famous separation idea that we're all separated by a mere separation. Okay, so that's the Travers and Pilgrim study. And in the late 1990s, John Kleinberg said, you know, this is all fascinating. This is amazing that people, the median hop count is 6 and everything. And yes, it's great we have a small world, but the real question is, how the heck do people do this? How do they, in a distributed way, navigate the social network? This is phenomenal that people can do this with no knowledge of the global topology. You don't know anything beyond a few characteristics of your neighbors. You know kind of how many people each of your friends knows, maybe, and you know some things about them. You know what their occupation is, you may know where they're located, those kinds of things. So how is it that we navigate the social network with so little information, with only local information? How do you do this? What are the properties of the social network such that we can? And how can we use this to perform search? So the finding is that local information can be almost as good as knowing the global topology and finding the shortest path just by looking at that topology. And this is really surprising. So we can call this the decentralized search problem, and lots of applications of this. You can imagine routing applications, you can imagine finding people in organizations this way, peer-to-peer file sharing, lots of neat things you could do with this if such a technology existed. Now, the answer to the question of how to do this efficiently, how people do this well, can be broken into kind of 2 categories. There have been 2 answers that have been posed. One is that, well, you route using homophily, using this autocorrelation idea, this idea that similar people tend to be connected. So if you want to get it to a stockbroker in Boston, you say, I'll give it to my friend who's a stockbroker. Or I'll give it to my friend who lives in Boston. Or even better yet, I'll give it to my stockbroker friend who lives in Boston. Maybe he knows that person. Or if I don't know a stockbroker in Boston, maybe I'll give it to a lawyer in Boston, because lawyers and stockbrokers tend to know each other. Maybe you think that. Okay, so homophily can be used to navigate. And John Kleinberg and Duncan Watts and co-authors have done some really nice work on that. The other possibility is, let's just give it to a friend who has lots of friends. Maybe he'll know, you know? So you give it to friends who are highly connected. High degree nodes can be used to navigate. So these lead to different navigation schemes. One says select the neighbor who is most similar to the target, and the other says select neighbors with highest degree. That's how you should navigate in this network. Now, Oscar and I said, yeah, this is crazy to have these 2 different ways of doing it. Let's combine them some way, some principled way of combining all the information you have. Want to incorporate both of these, and what's surprising is there's a really simple formulation of this that works really well. And that reduces to selecting the neighbor who is most likely to link directly to the target. Now it sounds really simple, but what's really nice is the derivation, the way we get there. So what we want to do is at each node, the ideal answer would be to minimize expected path length to the target. That would be your overall goal. So you want to minimize this value, expected path length, which is the sum of the path length itself times the probability of that path length. And that's, you know, a big summation. Great. The problem is, no idea what these are. Anywhere past here, we can't do it. Even if you had global topology, it's a big dynamic programming problem, not something you really want to do. So we only have local information. Turns out we can only estimate this quantity. Oh, can't possibly work well. Well, let's go ahead and try it. Maybe it does. In fact, this is really pretty easy to estimate. There are 2 characteristics, this probability and the degree. We know both of those things. Let's use this. We can estimate this probability fairly easily. Let's use that to navigate and see what happens. And if you've already visited a node, we're not going to go there. Okay. So the idea is to maximize this quantity If degree is constant, you're just maximizing this probability, which is similarity-based navigation. And if there's no homophily, you're just maximizing k, which is degree-based navigation. So this pleasantly reduces to the two main approaches in the extreme cases. But what happens in between, which is the normal case? Well, here's what happens in between. Here are networks where we're varying the homophily parameter, so how much homophily there is in the network. And this is optimal, okay? This is perfect performance is at the top there in black. Red is expected value navigation, EVN. So this is in terms of how many of the searches are successful, and these are on networks constructed to have homophily and variation in degree. EVN performs surprisingly close to optimal, where you see degree-based and similarity-based navigation not doing nearly as well. If you look at the median path length, not just whether it gets there, but how short the path is, EVN has very short paths, whereas similarity-based and degree-based have much higher paths. This is an example of the kind of paths that EVN finds, an example of the kind of networks that we were testing it on. Here you started in this node here and said, find that path using only the information about homophily and degree of your neighbors. And so, yes, sometimes it bounces around and doesn't really find its way, but eventually it does and can find very short paths.
I mean, you do effectively have a breadth for search because you're going to zero if you've already visited a node, and I assume you've constructed connected graphs. So what do you mean by successful searches? Is there some length cutoff? And also, what about varying the diameter of the graph? I mean, is that also held constant because you're trying to model something that has the same diameter?
So we've run it on a surprising array of different graph generation techniques, and not really found much variation in the results. We've also run it on real graphs, on graphs like citation networks, where we've used the abstracts of the papers as the attribute, so we can look at similarity between the abstracts. And we don't. It's not just a matter of the. This is actually, I believe, the actual path examined, not the shortest path found. Okay, so we're rarely backtracking, rarely going to a node. We have to have that in there because occasionally you do end up back to a node.
But then you had the proportion of successful searches. So what's an unsuccessful search?
An unsuccessful search is you can't find the thing at all.
After you run forever.
After you run forever, I mean, if it's connected and you.
Yes, we had something like 1,000 hop cutoff.
Right.
Yeah. So sometimes you just got to give up. You're not. And random here. This is random search. It's so rarely. Obviously, gosh, it obviously must be 100 node cutoff. Because here is 100 node cutoff. Here is the actual path lengths, and a factor of 20 roughly before cutoff. Yeah. Surprisingly effective. We were sort of saying maybe it's going to do slightly better than these other two because it's really just a trade-off of these other two, and actually does. It's not like it tracks along here. It's that it is consistently either equal in extreme cases or much further below. All right, that's navigation. So the last thing we said was, hey, we can navigate in these networks using properties that exist in the network. Shouldn't we be able to create those properties in order to index a graph in a way that's useful to find short paths? Suppose we want to find short paths in a network that doesn't happen to have homophily in its attributes. Maybe we could induce homophily in some of its attributes or put new attributes on it such that we could find short paths when we needed them between arbitrary pairs of nodes. So we wanted to use the ideas that we'd found about how to navigate in order to index graphs. That's weird. It says navigation. It should say index. So we want to exploit these short paths to do things like find the most central nodes in networks, or any of a large number of path-based measures. We'd like to do it for very large graphs where, for instance, all pairs shortest path isn't something you want to try to do. So we came up with this idea of a network structure index. That is something where you have a set of annotations where every vertex has some value, and a distance function where you can compare two of these values to get an estimate of path length between those two nodes. So any two nodes we can look at and say compare their scores, compare their index values, and get a decent estimate of path length. So as an example, let's say we have a graph here with a set of nodes. We're going to put values, in fact, sets of integers on these, and then if we pick two nodes, we can compare these values and say how large of a distance is there. That gives us out a number, and we can say, okay, how large is that distance by comparing those index values? Or to other nodes, and we can compare their index values and say, well, gee, the blue circled nodes, those are further apart than the red circled nodes. That's the basics of how a network structure index works. And I'm going to try some really simple structure indexes. Then we could use that to do breadth first search and find paths, hopefully find them efficiently. Let's try the simplest idea we can think of, which is to create a set of contiguous zones in a network where these zones are mutually exclusive and collectively exhaustive. So we're going to partition up the network, any network, into a set of zones, and then we're going to do that many times. So here we have red, which corresponds to the first number here. 2 is blue, red is 1, 3 is green. But we're going to do that many times in order to get a set of values that then is the index value for each node. And then we're going to use them comparing a distance function, compare them using a distance function, and try the zone index. We're also going to try another kind of index called distance to zone, where we not only have the values, but we have integers that indicate how far away you are from every other zone. More storage, but also it turns out more accurate. So these are the two we're going to look at, zone and distance to zone. If you compare them on, here we're comparing them what are called forest fire graphs, a very recent graph generation technique that is thought to, for instance, model the internet fairly well. If you look at the effectiveness of these network structure indexes, path ratio says how many multiples of shortest path are the paths that we find. Here, blue is distance to zone, green is zone, and then this is GNP, global network position, which is a network routing algorithm for the internet, which you would think would work really well because it's intended to find short paths. And it actually does not work nearly as well in terms of finding short paths. And it's also, in terms of the number of nodes you have to explore in order to find this short path, is that second graph. Again, DTZ does very well. Dimensions here are the number of zones, for instance, or the number of zones plus their distances that we have for these two NSIs. Now, how accurate are the estimates that you get? Would be another interesting thing to look at. Here is actual graph distance and annotation distance. It's a pretty good estimator of graph distance. You can fit a linear regression to that and say to yourself, just by comparing the values, not doing a search, but just by comparing the raw values, you can get an estimate of how far apart those nodes are. It's fairly good. Graph distance is shortest path, and annotation distance is just by comparing those two values. So you don't actually even need to do the search in order to figure out a reasonable estimate of how far apart those nodes are. Now, if you want to use that to then estimate centrality measures, again, you're doing constant time distance estimates between any pair of nodes. You want to use that to estimate centrality, and then you're going to look at the exact rank and the approximate rank shockingly good estimates of centrality. In other words, take the top of your ranked list and you've almost perfectly got the top of the ranked list in terms of centrality, showing you the most central nodes in the network. In terms of the design trade-offs of these different techniques, these are various ways that you can do it. All pair shortest path has the highest time complexity, but also the highest accuracy. You have higher time complexity for DTZ, lower for zone, but they're reasonably accurate, more accurate than some other approaches. And in terms of space complexity here as well. So more details about this in the paper, but overall, these give you surprisingly good answers for substantially lower space and time complexity. Now, we can do some really fun things with this. This is the sort of intriguing stuff you can find out once you can do this on really good graphs. So we took the actor-actor graph, the graph of all people who starred together in a movie. And then this is from the Internet Movie Database from 1970 to 2000. And we said, who's the most central person in Hollywood? Anyone want to guess? There's an obvious answer. Kevin Bacon, of course, yes. Anybody else?
Sean Connery.
Sean Connery, okay. Anybody say Rod Steiger? It turns out, if you look at the Internet Movie Database for all time, Rod Steiger is the most central person in the Internet Movie Database. We looked for 1970 to 2000. A little bit more modern, okay.
Doesn't it make you doubt your methods? It makes me doubt it.
So, it is in fact President Bartlett. Martin Sheen. Martin Sheen turns out to have starred in a shocking number of movies across a vast range of genres and, I will say, quality of movies. And he has an enormous number of co-stars. You're not going to get the big movie star here, you're going to get the prolific person. It also turns out that Martin Sheen started his movie career in 1970. Now, some of these other people are really surprising until you go looking at the data. Michael York, you say to yourself, Michael York? Man, how could this possibly be? It turns out the Internet Movie Database has an enormous number of foreign films in it. So if you're asking for closeness centrality, how close are you to lots of other people? You don't want to be stuck in one of these communities, you want to span communities. Turns out Martin Sheen has, and Michael York definitely has. He connects into the whole sort of British film industry and some other industries as well. Jürgen Perchnov, you may have, if you know the movie Das Boot, he was the captain. He has a very large, big career. And some of these other people, you'd recognize their faces even if you don't recognize their names. Kevin Bacon is unfortunately 554. There's also an embarrassing fact that we learned about the Internet Movie Database when we did betweenness centrality. Betweenness centrality says of all the shortest paths in the network, how many of them go through a particular node. So these are choke points in the network, people who connect up communities, explicitly connect up communities. Who do you think has the highest betweenness centrality in the Internet Movie Database? You'll never guess. This man is Ron Jeremy, who it turns out is a prolific adult film star, who has done a lot of crossover films as well. He has starred in, shall we say, legitimate films as well. And we're trying now to purge the Internet Database, our copy of the Internet Database of these films, in order to get a more sort of realistic estimate of who we would think might have high betweenness centrality. However, if you go down the list a little bit further, Gerard Depardieu, a very well-known French film star who starred in a fair number of American movies as well. Same with Stellan Skarsgård. Martin Sheen shows up pretty high. There is a pretty strong correlation between betweenness and closeness centrality as well. So, putting together these ideas.
By the way, I just noticed a woman in the list. Nina, I suppose.
Nina Hartley is in fact an adult film star as well. I found out.
No, I just noticed that in the previous list there was no woman. Was there?
Whoopi Goldberg is about the only woman in the list, I think.
Oh, there she is. Okay.
Not many. Yeah.
Yeah. It's amazing, isn't it?
Yep. I think in terms of maybe the sort of spanning nature of some of these men is that they're allowed to have because of less sexism allowed to have a wider range of things. We may pigeonhole women into particular kinds of roles. Whoopi Goldberg not. She's a great example of somebody who's done all sorts of different kinds of movies, serious and I mean, comedy and not comedy. We tend to think of her in terms of comedy. So last slide, connecting the dots. Statistical modeling techniques that we discovered for identifying relational dependencies, came up with to discover relational dependencies. Then we want to use this idea of relational dependencies, particularly autocorrelation, to find short paths in graphs. And then create these relational dependencies, these autocorrelation relationships, so that we can index graph structure. And then what we can do is use those indices to create new measures on graphs that can be used in statistical modeling. It's just, once it all kind of came together, it was a really nice cycle. It was a bit unexpected when some of this work started. I used to say to some of my students who are working on the indexing stuff, saying, ooh, this is pretty far away from what we've been doing, but gosh, it's so fascinating, we'll pursue it anyway. And then it ended up paying off in unexpected ways. We have open source software that implements almost all of this. The NSIs are just going in recently. This is some screenshots from our software. It's available on the website. And finally, you can go here for additional information. Thank you very much.
Just like I didn't understand along the way. When you were talking about the zone measures, you said you divided things up many different ways or many different times, and I wasn't sure I understood.
So the simple thing you could imagine doing is you lay down a set of random seeds. And you grow out from those seeds until you encounter already labeled nodes. And you do that for many different times, yes. So the dimension on the x-axis of those graphs was the number of times you did that. It turns out that the simple way of growing, which is for what you'd expect, sort of grow out to all neighbors, performs horribly. But
you mean
instead,
if you don't take the labeled data into account?
excuse me?
You mean if you don't take the labeled data into account?
No labeled data here for indexing a graph. It's just the graph structure alone. So what we did instead, rather than saying, oh, we're going to take the node, we're going to take all neighbors and label it the same as the seed, what we did is choose one neighbor only and label that with the label of the seed. And then do that for all the possible, all the seeds. And then go back to each group, pick a node randomly, and pick one neighbor and label that with the label of that.
Is that because it corrects for degree?
Actually, I think what happens is you create these long, stringy zones which provide paths to other nodes. We don't actually know why it is that this approach works a lot better. It also produces much more consistent sized groupings. There's still some variation in size because you end up being limited in growth sometimes. But growing to all neighbors, it can be, you hit a high degree node and suddenly there's one dominant zone in the collection, and that's not a good thing. You want more even groupings. We're still figuring out why these things work well. Literally, these are some of the first things we tried, and the fact that we can outperform global network position, which is a standard approach to decentralized routing on the internet, is a real shocker. Something is either not right with GNP. We're sure we've got the right implementation too. We're using the code of the author. But either something is different about our graphs, which doesn't seem likely because these graphs, this graph generator we're using is the best current model for generating internet-like graphs, which is where you'd presume that the routing algorithm would perform well. Or there's something that's really not known about GNP, or we got lucky to come up with two methods that significantly outperform. Still active area of work in my group.
Tell me again what in-betweenness means.
Oh, betweenness centrality says the way of thinking about it is choose every pair of nodes in the network, find the shortest path between them, and then betweenness centrality is the number of those shortest paths that go through you, go through any particular node. So some nodes that are on the periphery of the network would never have a short
And
path.
what would that mean in terms of actors?
It tends to mean people who sit at the intersection of otherwise disjoint.
What is the path between, so,
Oh, from actor to actor based on co-starring relationships. So when actors have starred together in a movie, there's a link between them.
Sorry, is that starred together or appeared together?
Appeared together. Thank you, yes. For those, I take it the difference being only the well-known actors or any actor?
Whether they're well known isn't relevant, but whether they have a lead role versus a
Yes,
minor
so this is
role.
appeared together. You can just appear in a movie as a cameo. If it's credited, it'll be in the database.
Let me go back to a question I think that Gary asked and you answered, but I didn't catch your answer. So when you were building these decision trees, so one of the questions you asked about, let's say the broker example is, like, what is the size of the firm? Was it bigger than 20 or something? And so I would assume, for example, that all 20 brokers in that firm have that attribute that they're in a firm of size 20 or larger.
Yes.
Right, and so they would all go left or right. So when you came to a leaf node, you would have, let's say, 50 samples, but they're not 50 independent samples. So now how do you make a distribution on that node for whether or not some fraud will be committed?
For the probability estimation at the leaves,
Yeah.
we are using we are treating them as if they're IID.
You're still
For
treating
the
it-
choices of whether a particular split, how to rank the possible splits,
Mhm.
and how to decide whether a particular split is statistically significant,
Mhm.
we are doing a somewhat better test that accounts for the autocorrelation.
Okay.
We're doing an adjustment, which I'm still not happy with, but I think it's doing better than being completely naive about it. Yeah.
Okay.
Now, what you'd expect to get is a drop in performance if we're not accounting correctly for autocorrelation in the leaf estimates. And I think you're right that we're not doing that appropriately, but we're getting fairly good accuracy on test data, separate test data, and there are a few ways we could be being fooled, but I don't think by any big margin. It's doing the right accounting for this is very tricky, and we're still that's one of the main areas that we're looking at. There's just a whole can of worms here, and really doing this well. We're taking some techniques from spatial analysis, where the people have been dealing with autocorrelation for quite a while. We're also trying we're doing this right now, for instance, some Monte Carlo work, where we're saying we're going to model autocorrelation, and then of course we can actually create data sets with particular levels of autocorrelation and see whether these other dependencies are really there. Because what autocorrelation tends to do, and there's some other effects, one thing we call degree dependence, that tends to fool you into thinking that some other relationships are significant when they're really not, because you don't estimate variance correctly.
And I guess, and a related question then would be that in that case, have you possibly tried bagging on your data to create your trees? Because
The actual results you saw were bagged trees, 10 bagged trees.
okay, because the bagging would get rid of some of it, because not all 20
Some
of
of the
those
variance.
brokers of size 20 wouldn't be in the data, so you'd see only a random subset.
Yeah.
There'd still be correlations.
It's not going to really reduce it that much, but for large firms, so you have 16 rather than 20, or 18 rather than 20. Not a big deal, but yeah.
But researchers in many fields have failed to nail down the effective number of independent observations problem, so.
Yeah, this is
It's not solved
huge-
all over the world.
No, and the fascinating thing is that I rarely find data sets where I really think the IID assumption is valid. And, we're looking at this and saying, oh, we need to account for it because we can. We actually have the underlying data to account for autocorrelation. But I think almost every analysis of large data sets ends up, there's an autocorrelation problem built in there. You're just pretending it's not there. So I think once we're more confident that we've got decent solutions to this, I think we can then start going out and looking at more sort of traditional data sets. I look through the UCI, University of California, Irvine, data set repository, and I look at these and say every one of these is essentially derived from a relational data set, even though we're pretending it's not.
So it seems like there ought to be some connections in both directions between your navigation work and work on focused web crawling. In particular, the web crawling people, and this is true back to the original Google crawler, about which paper was published in '98, accumulate information as they go. So
Yeah.
they don't have a static metric. Rather, they're gradually computing an approximation of PageRank, and they're using that. And I've thought for a long time that you should be able to learn as you go through regression or reinforcement learning, which kinds of edges are worth following
Right.
for a particular kind of search.
So Andrew McCallum.
In the other direction, you want to, some of the things you're doing might be of interest to the web.
Right. So there's some nice work by Andrew McCallum on when he was doing work on Cora, his system for crawling the
Yep.
web and finding citations, an early thing before CiteSeer was around. That he actually did focus web crawling with reinforcement learning. So great idea that and they were doing very specific. They were looking for PDF and PostScript files.
Yep.
And so the question is, let's as we go find the types of
Not
links.
just any PDF and PostScript files, right?
Yes,
Scholarly papers.
CS papers.
CS
right,
papers,
yeah, so they were sort of, it was a beautiful reinforcement learning kind of setup, because you would eventually get to one of these papers and say, oh, okay, great, it's a CS paper and it's PostScript, and so then we have to appropriately reward the links that we followed. They didn't get a gigantic gain from doing this. There were some very early gains, and then it was sort of, there's a set of things you want to ignore, and then from then on, it's a tough problem, as I recall the paper. But yes, anyway, on the larger point that you're making, I agree with you that one way of thinking about this is, could you accumulate information about autocorrelation? Could you sort of estimate these autocorrelation dependencies and then be able to exploit that later to say, oh, well, I know what target I'm going to, and I found that this is correlated fairly highly with that, with some characteristic of the target. Haven't thought about that. It's interesting. We started out with this as a fairly theoretical problem, that sort of Travers and Milgram thing. How did this happen? And now we're starting to look for applications of it. Any other questions? Yes.
One kind of general question. Did you look at spectral graph theory and what it gives you, for example, computing distance and I don't know, various applications?
So not for the distance estimation work, but for some clustering work on graphs that Jen Neville, actually, one of my students, did. We were looking at whether you can use the link information as an extra source of data about what entities to cluster together. And some of that was based on spectral methods. In terms of the distance estimation, no, we haven't, and it's an interesting sort of future direction to go in. Anything else? Well, thank you very much. I really enjoyed it.